Hello, thanks for having me. I'm really excited to have the opportunity to speak here on a topic which is very core to my heart and my interest, namely statistics for engineers. Yay, statistics. Who loves statistics? Yeah, that's very nice to see. So before I dive into all the math things, I just want to say a few words about myself. My name is Heinrich. I live in Munich at the moment, and for people who are not familiar with Munich, it's a city in the EU, still in the EU, and I'm very happy to be a member of that great community, and I want to express my really sincere sadness about the UK, who has expressed their urge to leave it, and I've also spoken to a few folks here who are directly affected. It's really a sad event to see them leave. Apart from my national identity, I have also a cultural identity, which is I was a mathematician. I come from a town called Academia, and I am here a refugee in the monitoring community, and I want to thank you all for welcoming me here. And it has been a very warm welcome. And also, this particular place at the conference underlines this a lot. It's a very, very nice atmosphere, very interesting talks, and I can relate to many of the messages which were put out here. So, but remember, this sign, PhD, is actually the symbol for the refugees from Academia. Right. So, what I'm doing here, at the moment, I'm working for a company called Seconus. You might have heard of it. It's a monitoring analytics platform, and I'm the lead on the analytics part. So, statistics for engineers. I have been asked to talk about this in the last year a few times, and I actually did so, and I also put a lot of things to writing. Most notably, there has been a recent article of myself in the ACMQ, which is a great magazine, which is available online for free. So you can read that thing, and these slides will be on Twitter, so you will have the opportunity to find that article and also read about all the topics that will be covered here. I will use that shamelessly as an excuse to skip over topic and go fast. It's really, really tough to distill a lot of statistics and stuff like that to a 30-minute presentation. So please look at those blog posts and articles to learn more. There will be also a 3-hour version of that talk at SRECon in Dublin in a few weeks. So if you like, attend this. But of course, as long as I'm here, feel free to come to me and talk about it. And maybe I will have time for questions later in this presentation as well. Okay, so I've been told that mathematics can be a little bit dry from time to time. And to make it more engaging, you should always put it into a story and make it personal. So what I want to do is I want to tell you a tale of API monitoring, like a problem that many of you will be able to relate to, and in the very concrete form of a fictional web store, which I call Attic. It has a great API, which is just a web interface it exposes. It has a catalog, which the users can see. And it has this funny thing that they lose money if requests take too long because users get offended. And they want to monitor this API. And I will tell you through the tale how they started, what they tried, and what kind of mathematical difficulties they ran into and what you need to know in order to make sense of your data. So what do they want to do? The main goals of monitoring are to measure the user experience and the quality of your service. Is the service up in the very, very least, but also how do users feel about the service? And you can, with good monitoring, you're able to determine financial implications of service degradations, and you can then take these metrics to define sensible service level targets for your dev and ops teams. As I said, I'm coming from the mathematical side, but I feel that it's not failures happen, and it's really about defining sensible measures of how much error is okay and how much at the end, often financial implications are suffered from the errors that happen. And to give you a basis for your discussion, that's one goal, a key goal of monitoring APIs in particular. Okay, so the very first step, if you approach the problem of monitoring a website or an API in general, is a theme of external monitoring. So what you might do is configure a synthetic check that reaches out to your API once every minute and looks if this request is successful, if it was an error, and you might measure the latency of that request. So if you do that with our tool or other monitoring tools, you arrive at charts that look like this. This kind of charts are great if you want to measure pure availability, so is the service actually reachable, and you can use it to alert on outages. It's bad, however, to measure any kind of user experience. Remember, you just have a synthetic request, so the only thing you learn from that how you basically serve the robot. So there's not a single user involved with that request, and there's also more doubt or more problems with this kind of monitoring in that these request patterns are often very easy to cache or to predict. So with high probability, this one request you're making, maybe to your home site, will be served completely out of cache, and the only thing you're measuring there is the performance of your network. So this kind of graphs are actually very often seen. So you have this kind of spikes and otherwise like a measure here. There's another thing which I want to point out here is that of course, this kind of graphics are always produced with Synchronous. I will make no excuse for that. But one thing, we use this kind of bar-like things, which I like, in compared to these line charts we have seen a lot. The one point here is that the line charts always suggest a kind of continuity between that. So if you've gone from this point here to that point here, these are just two measurements. At that minute, you had that duration. At that minute, you had that duration. So there's absolutely no sense of continuity between those two measurements. And I really have to just move my mouse every other minute. And that's a little bit of a misleading visualization. So if you are looking at line plots, always ask yourself, is it really justified to draw a line which has this sense of continuity, or is it not like better served by kind of these dots or scatter plots or other kinds of visualizations which show you the true data? You don't want to be misled by your visualizations, you want to see the actual data points. And there's a problem which is way, way more severe than just the drawing of lines. That's actually the phenomenon I call spike erosion. So this is the same graph on a much larger scale. So you see like April to May. So this is actually like good months, a little more than a month. There are, I don't know, very, very many measurements which were taken in this whole month. So you have to calculate the number of minutes that were in this month, which is a huge number. Or a big number. It's certainly more than the actual amount of pixels you have available on that screen. That means every time you look at graphs which have more than like an hour or this kind of small time periods, you will see aggregation all over the place. And what I did here is I used what we call a histogram aggregation or a min and max aggregation to make you aware of how drastic the effects of aggregation are to your data. So what you see here is the usual view that many tools will present you. What you will see here is how the same graph goes on. And in addition, I have drawn the actual measurements as a kind of heat map. So it looks a little bit like dirt. We call it actually a heat map or a histogram. But the essence is these are your actual measurements. There are very, very little points sprinkled all over this map. You see you have a lot of measurements up here. So this other line is the actual 1 day maximum latency you have been experienced. And the points down here are like other measurements. And for each of those values in the line graph actually represents I think a 1 hour average of all measurements that are made. So you're actually seeing a compressed information of 60 data points. And that's a drastic thing. So our clients tell us we can't do capacity planning on averages. So if you look at graphs like request rates, you don't have any idea of your maximal latency if you're looking at a chart which is aggregated in averages. The actual data distribution will be all over the place. And there are certain metrics which are okay to be averaged, like disk utilization, stuff like that. But for many things, especially the volatile metrics, it's very, very misleading if you look at those slides at a large time scale. And it's a problem that like many tools have, and it's not so easy to address. They're actually like, you cannot blame the vendors or the tools, because shipping you all the data points might involve sending 50 megabytes of JSON to your browser and then crashing your browser because your rendering engine can't do it. So that might not be a smart choice either. Sometimes it's just better to get a rough idea. But keep in mind, if you're viewing timescales of weeks, you're just seeing a very, very thin shadow of your actual data. So part 2. So after they have done external monitoring, which is a great thing to do, they said, well, okay, how can we do better? We need to understand our API more. We need to serve actual users. We need to measure actual users. We cannot only measure robots. So they started log analysis. And log analysis is also a very great thing. So what you do is actually here, you write to a log file, the time of completion of your request, or the time where the request went in, the duration, like the request latency, and all kinds of further metadata you have attached to that. Maybe the document you're retrieving, maybe a session ID or whatever. It's a very, very rich source of information. It's pretty trivial to do instrumentation with log files, just printf. That's very, very cool. And you can compress very, very high dimensional data into log files. So you cannot compress it, but you can store it. You have a lot of rich information about the requests. And here's my little attempt to draw the kind of numerical information you get out of there. This is the UML version of the API, the internal API. So you have a user making a request at a certain time. There's a request latency, and there is the response send out. And all this information is contained in your log line. So every of these blue lines would be a user making a request, coming back. It's the information, the numerical information contained in a log line, which is great. It's the actual users you're measuring. It's like the best kind of information you can have about the API. The problem here is, and it's common to all log tools, it takes very long to retrieve the data again and to store it actually, because the format is so inefficient. It's inefficient as in big data. It's one of the really single ways, or the rare ways, how you can actually produce petabytes of data. And if you're just looking at 1 year or 1 week, you have to digest all the log files. So it will be slow, and there's no way around that. And for that reason, also expensive. And if you do very, very high latency APIs, high volume APIs. So I put the example of a web store first, but APIs are everywhere. This is a very, very universal topic. I mean, you all know about services and stuff like that, so microservices, but also your layers in your software architecture, like syscalls. Syscalls are an API, block devices are an API. APIs are everywhere, and you might want to also capture latency information, capture performance information, all of these kinds of APIs. And imagine doing syscall latencies with log files. This is not going to work well. However, it's great if you can afford it. So if your API is low volume enough, then by all means do this kind of logs, write out the accesses as log files. So here on this slide, I have tried to digest the numerical information you get out of the logs and the API usage in a more concise way. And give you another mental model of how to reason about your API. So in the next slide, I have the construction of that. So it is very easy. So if you have this UML version and you're all with me, what this diagram here means. So what I want to do here, or what I've done here, is to use a second dimension and put it to use for us. So instead of showing the latency as a here time stretch, I will rotate the latency and put it on the y-axis. So every request will now be represented by this kind of vertical lines, yeah, that's correct. And the height will say how long the request took. And here's another little bit about math and this kind of subtleties of monitoring that I want to point out. You have two choices here. You can retire the thing on the left or the right. You can base it on the time the request went in or the time the request went out. The problem is, if you are right here at this point in time and have a request in flight, there's no way, I do not know how long this request will have taken. And if I want to give you the full information, if I want to put that slide on the other edge and base that thing here, I have no way to produce that graph at this very point in time. And these are, I don't know if I expressed that really clear, but there's a trade-off between timeliness of your data and correctness of your data. Putting the chart on the start time, I have no way to produce correct data. Only by putting it on the request finish time, I have the full data available that I want to plot on a certain point in time. So here is another visualization of your API. And by that, if I now have my math hat on, then I will say, well, great, I have so many tools how I can analyze this kind of patterns, this kind of data I have available from the API. So I might project the data to the y-axis and put a histogram here. So this is for what we call a marginal distribution, and I will have a probability density function and a maximum likelihood estimator of certain probability distributions. So, and all kinds of statistics I can do with this kind of boundary distribution. As a mathematician, I see a kind of a arrival rate process, and I can mumble Poisson distribution and just attack it from this angle. And if I'm really fancy, I can remind myself that a request is not on CPU all the time or served all the time on CPU or on like just the machine doing work. It might actually be in a queue for a little while. And there are fascinating problems about like balancing concurrencies and request rates and determining capacity, which you can analyze from the angle of queuing theory. And there's a great book by Baron Schwartz about queuing theory, which I want to advertise here. It's really a great read, and it's yet another mathematical angle you can have on that. If you're talking to your sales and your marketing team, you will, however, have a pretty other view on this API. Because they will not say this is a percentile or mean value. These requests are actual people doing the requests. So, and depending on how you serve the request, they will be more or less happy. So some people will be served, they will be super happy. The Google bot got served, it's okay, it isn't happy or not, it just indexes your site. On this guy, you actually just pissed off really hard. He's leaving, going to the other website, or it's going to Google again and then take its business everywhere else. So requests are people, those latency actually matter, and just putting percentiles on it and mean values on it often hide the fact that you're actually talking about people, their emotions like hatred if their requests take too long, or money if they go somewhere else, right? So you really should care about this kind of things. Okay, so what can you do? What can you do next? So what many people do with these kind of things, they need to find a way to compress the information in the log files because they're just too large. And what do? They take the mean value. And here we come to a topic of my core expertise, calculating mean values. That's always fun. So what you do is you actually sum up all the values here, and you divide by the number of samples you received. And if you want to have a physical analogy of that is if you have a lever, I think that's the right word, it's like basically a kind of thing that shakes to both sides, and if you put equal mass on all of those things, then this will be the equilibrium supporting point. So this is the physical explanation of a mean value. And what the physical explanation actually will show you pretty easily is that there's one point on this lever which is way outside, it will skew your whole distribution to the one side. So it's very easy to affect mean values to the top, and it's also very easy to change mean values to the lower end. This is, again, a problem with caching. If the static store is measuring all requests, many of them will be cached, and you will have very low latencies, and the mean value will not be a very useful thing. So, for example, here's how that might look like in one of the examples that we have. Here you have outliers all the time, and here crazy things happen on the boundaries. I might ask you what it actually happens, but it takes too much time, so I will just say it. There's actually nobody on this side. It's night, and there's 4 requests, and it's Google indexing your site, and they have really bad cache hit ratios, so the mean values are way off. And this is how that looks. Right. So what you have to do for this request latency monitoring is you have to first select the reporting period, and I didn't really spend a lot of time talking about that, but it's also a very essential step. Then you can calculate the mean value, and there you will have if you have measured actual people, it's very steep to collect, store, and analyze, but you have skewed your distribution, or you have compressed an awful lot of information into one single value, and this is always a very problematic thing to do. And I was asked, how much time do I have left to present? Nobody knows? Maybe 15 minutes? Okay. Right. So this is some ways how to do better. There are ways to address like the outlier problem by, for example, taking median values instead of mean values. You can actually go a little bit fancier with truncated means, idea being you just throw away minima and maxima and then take the mean value from there. And you can also try to collect deviation measures, but this is also a very delicate topic. Okay, here's the next idea. So people are very aware that averages are a problem, so what they turn to next is percentiles. What is a percentile? Just really quick, the basic idea of a 50 percentile is it's a value that divides your data set in a half, bottom half and the top half. The idea of a 99th percentile is you divide your data set into a top half and the bottom half of 1% and 99%. A little thing about percentiles that not many people know is they are actually not unique. So for example, in the 90th percentile, every value in here between this whole two things qualifies in the 90th percentile. So be a little careful with the actual definition. If you look at Wikipedia, there are 8 different ways to make percentiles unique. You never really know which one is the right one for you. And I'm going a little bit fast here, but I want to come to also to later slides. How the percentile monitoring method works is first you have to select this reporting period, which tells you how much values you're actually putting in a bucket. Then the second thing you do is actually to compute this latency percentiles, you can just sort the data and you will have a really quick way to compute the percentiles by just then counting which nth of this values you need. And then you calculate for each reporting period, again, this choice is really essential, like how much time on how many values you put into this percentile. You calculate the 50th, 90th, 99th percentile. You store that as a time series, and then you alert when percentiles go over a certain threshold value. And this is actually not a bad mean at all to judge your API, user happiness or your API performance. You measure the actual requests. You have a way to do so without collecting massive amounts of data. It's robust to outliers, so the single spikes we're seeing are going away. The two drawbacks are you need upfront choice of those percentiles, and it's not always easy to tell which ones are precisely the right ones for you. And then the very last point is percentiles cannot be aggregated. And I will come to that point again. So here how it looks in practice. Here's the 50th percentile, so this is what directly competes with this guy here, mean value on median, and you see median is a little bit nicer. You see this 90th percentile down here might be a good way to alert on, like 90% of your users were happy or reasonably happy, and the 90th percentile, you know, okay, with very few users, I have actually just not done a terribly good job of serving them. But it's, yeah, you have also these terrible problems at night, and it's just also a little bit not very intuitive what the message is if you look at a graph like that. Right. So, and now I want to make that very last point on the slide again, which is percentiles cannot be aggregated. This is a very severe problem with percentiles. The median of two median values is not the median of the total sample set. If you have two nodes and compute the median, which are serving the same API, and you're computing a median on that node and a median on that node, you will have no way to know the total median. If you are computing a percentile over a 1 minute period and over another 1 minute period and in total 5 1-minute periods, you have no way to calculate the percentile of the 5-minute period there. So with percentiles, to do percentiles correctly, you have to know which kind of aggregation levels, which kind of aggregation periods, and which percentiles you need. You need to know all this information upfront, and you need to collect all of them and never ever roll them up. Because the average of percentiles is just completely meaningless value. It's like, it doesn't tell you anything. It tells you some ratio was here and another one was there, and you will have no idea what it actually means. So it might be okay to get a rough idea of your actual data, but keep in mind how misleading averages can be. But try to keep your percentiles non-aggregated. Store them all, so you will have meaningful values. And again, I mean, if you are tuning some SLAs, you never know which kind of percentiles are the right ones to look at. Do I do 99.9, can I serve 99.9% of my users well, or more or less than that? So if you do all of that, then percentiles come and with a significant cost. And we have also written about that on our blog. Okay, great, just 2 minutes. That's good to have the half of your presentations compressed into. So what, yeah, it just happens. Okay, so how can you do better? And let me go give you a little survey. So what we propose as a solution to that problem is actually histograms. And this is what many people use internally on their agents to compute these percentiles. So what you can do is take this request latency distribution and chop into latency bands. And for this latency bands, you just count how many samples there are. And here we'll have the familiar picture of a histogram. And it turns out you can actually store histograms. And you can do calculations with them. And you can store them extremely compactly. Compared to logs, this kind of histogram information is pretty compact. And it can be trivially aggregated across time. So if you have 5 histograms across 5 minutes, just add the counts. If you have 5 nodes, just add the histograms. So by storing histograms, you have the ability to do all kinds of slicing and dicing with your data, plus you can still derive all the relevant measures for you. You can derive all kinds of percentiles, you can derive averages and all kind of that with a little bit of reduced precision. This is the price you pay. Right. And you can actually visualize your API performance or your API usage. This is a histogram heat map representation of the API actually served by many nodes. This is search metric histogram, so it aggregates data from all nodes serving the web API across a period of 10 minutes, and it shows me this data as a heat map. So, and what you can see here, we have one line down here, that's the cached responses, and then you have like kind of lines going down up here. These are, there's actually a problem here. You spot it, the request gets slower with time. So you have a bug in your web service which causes this. And I would argue that it's more intuitive if you look at the heat map. You can still derive all kinds of other measures from it. So you can do the mean, you can do the percentiles, you can do the rate, like count how many samples are in the histogram. And you can do actually better than that. So this is the line that's, the number is arbitrary, but say this is 5 seconds. This is the moment where your users really get pissed off if you're serving them lower than that. This is where they're at their phone and they're saying, go faster. You can just count the number of users you have pissed off. And this will be a very meaningful metric for you. So this is kind of the quest, and I think one of the things we should strive for as a monitoring community, to search for more meaningful metrics which are directly meaningful to you, which directly measure implications to your business. And like in this example, you directly see the 90th percentile was not so bad for that, or the 90th percentile, right? It was not worse than there so much, but actually the volume you were serving here was much higher than it was when you were serving here. So the financial implications of that 99th percentile being over a certain threshold value was much higher than it was down here. So you really need to correlate the volume you're serving with the quality of your service in order to derive actionable information that is interesting to your boss. So that's one thing. And the other thing you can do, you can just count the total users you offended. That's also pretty awesome. So at the end of your day, you know, like 4,000 people are actually mad at you right now. So that was fun to know. Great. So I will close with this. A few takeaways on this slide. Keep your data, strive for meaningful metrics, and thank you very much.